Hello everyone, I'm Li Yangsun from ByteDance. In this video, I will talk about our work of joint adaptation of video rate and playback speed in low latency live streaming, which was done during my PhD study in New York University. First of all, I will do a brief introduction to low latency live streaming, and then talk about the potential challenges. Followingly, I will discuss about our main contributions and finally conclude our work. In a live streaming system, after a video frame is captured by the camera, it will be uploaded to the cloud server. After the process of transcoding and packaging, video frames will be delivered to the end user's devices. As shown in the figure, the time gap between T1 when the frame is captured by the camera and T2 when the frame is rendered on the user's devices is the latency. In a low latency streaming system, the time gap between T1 and T2 is very short. Here we show statistics of some existing live streaming applications like YouTube Live and Facebook Live. We can see that the average latency of them are about several to 10 seconds. When compared with TV broadcast, which is shown in the last row in the table, we found that live streaming applications still lag behind the TV broadcast. One example is when users are watching the same event, the users who are using live applications might hear the cheering from neighbors before they see the glow on their screen. So we say that latency is an important QE metric in live streaming system. Can we reduce the system latency in a simple way? I think the answer is no. Assuming the figure is a screenshot of the system at time t, and the pointer shows the time of the frame which is being processed by the server. All the gray parts are what will happen in future. Then, a client can choose a time on the past of server time to watch the video, and the blue part means what has been watched by the user. The video content in between can be divided into three parts: client buffer in pink, server sending buffer in green, and data on the network in yellow. From the figure, we can clearly see that latency is the summation of all the three parts, which means short latency leads to short buffer lengths. Following the conclusion, with short latency, we get a short buffer length, which leads to lower video quality, more video rate fluctuation, and a higher risk of video freeze. Except short latency, all of these are not what we want. On the contrary, to get better other QE metrics, long latency seems necessary. So the challenge here is reducing latency and improving other QE metrics are contradictory. Our goal is to reduce latency with minimum influence on other QE metrics. We start from describing the model of a live streaming system. Given the initial parameters, the rate selector will choose a video rate to download. After downloading, the system state updates, and then the video rate selector will choose a video rate for the next video segment based on the new player status. And normally, the adaptive bitrate algorithms work behind the video rate selector. Differently, what we propose in this work is to not only control the video bitrate, but also adjust the video playback speed for the player. The motivation of doing so is to achieve better latency and buffer control. First of all, for video buffer, the chosen video rate affects the inflow rate. Higher video rate leads to slower inflow rate. On the other side, playback speed controls the outflow rate. So we found that the buffer control is jointly affected by both video rate and playback speed. In addition, in the definition of the QE of a live streaming system, there are several terms are directly affected by the playback speed. Therefore, in this work, we propose to jointly adapt video rate and playback speed to balance the system factors and QE metrics. There are some works about video rate adaptation for low-latency live streaming system, but only video rate is adapted without latency control. Some other works consider the playback speed control, but the playback speed and video rate are adapted separately. They might suffer to local optimal. In our work, we propose both model-based and model-free solutions to jointly adapt video rate and playback speed to achieve global optimal performance. In the model-based solution, we consider the video rate and playback speed adaptation as a trajectory control problem. If the system dynamic is linear and the cost function is quadratic, the problem can be solved by linear quadratic regulator efficiently. However, in a live streaming system, the requirements are not satisfied. In this case, we adopt iterative linear quadratic regulator, which is designed for nonlinear system to solve the problem. More specifically, to conduct video rate and playback speed adaptation, given a system state, we first of all predict future network bandwidth and solve the control problem using LQR. The solution we get is a control sequence for several future steps. To reduce the effect of prediction error, we adopt an MPC-based strategy in which only the first action pair is conducted. After taking the action, the system state evolves to a new one. Then, the same procedure will be applied to generate the control for the new state. This is a practical implementation of the model-based solution. The second solution we propose is a model-free solution based on reinforcement learning. The figure shows a structure of a queue network where the input is a system state, including both temporal sequences and scalar values. The output is our control action of both video rate and playback speed. If we have 6 available video rates and 7 levels of playback speeds to choose from, then there will be 42 combinations in total, which makes the action space large and less efficient to explore. Therefore, we adopt a new architecture, branching dueling queue network, to deal with this issue. The branching idea is originally proposed in AAAI 18, which can optimize the control of each dimension with a degree of independence. In our case, we consider video rate and playback speed as 2 dimensions. Based on the system state, a shared representation is generated. After that, each dimension of controls will generate outputs in different branches. By doing so, the action space exploration becomes more efficient. Overall, we use a table to describe the same and the difference between model-based and model-free solutions. First, model-based solution is a detailed model for the system. However, model-free treats the system as a black box. In addition, explicit bandwidth prediction is not required by the model-free solution, but long-term training is needed. Both of these 2 methods can jointly adapt video rate and playback speed for different QE definitions. To train the model-free reinforcement learning agent, we use a 4G cellular dataset with 270 traces. We assume 6 available video rates and 3 possible playback speeds are provided. For BDQ, benefiting from branching architecture, 7 levels of playback speeds are utilized. Video segment is with 1 second and delivered in 200 milliseconds chunks. For benchmarks, we choose to compare with Pensive, which is a reinforcement learning-based rate-only adaptation algorithm. Stylian, L2A, and LOL can adapt video rate and playback speed, but not in a joint manner. Then, LQR is the proposed model-based solution, ILQ star represents we use future network oracle to replace bandwidth prediction. BDQ is the proposed model-free solution. ILQR star with future network oracle represents the offline optimal solution. The figure compares the system performance of ILQR star under two different QE preferences, rate preferred and latency preferred. The video rate figure shows high video rate can be selected when rate is preferred. Then, if low latency is preferred, ILQR star can choose to fast playback to reduce the latency when network is stable, and accumulate buffer length by using slow speed when network is dynamic. The results demonstrate that ILQR star with future network oracle can optimally coordinate video rate and playback speed. The QoE comparison shows that the proposed model-based and model-free solutions can achieve better overall performance by jointly adapt video rate and playback speed. By adjusting playback speed, all the speed adaptation algorithms can efficiently reduce the average latency to below 3 seconds. For BDQ, even without future network oracle, but with more levels of playback speeds, comparable performance is achieved with ILQR star. We also find the model-free solution behaves differently than model-based by choosing rate more aggressively. While looking at average speed, we see that all the algorithms behave similarly except Pensive. As users have different preferences, we compare the algorithms under two QE settings, low latency preferred and high video rate preferred. Pensive can't adjust the latency for low latency preferred users due to the missing of playback speed control. The heuristic algorithms like Stylian and L2A cannot change streaming strategy due to the lack of QE awareness. While looking at ILQR and BDQ, we found that strategy can be adjusted in different scenarios to optimize QoE. Finally, we conclude our work in three folds. First of all, we say playback speed adaptation is important for live streaming to balance the trade-off among system factors. In addition, video rate and playback speed should be optimized jointly to achieve better QE performance. At last, our solutions can be customized for different user QE metric performance.